This is a talk about cryptography, but don't be scared. The most difficult part of this talk is, for me at least, is pronouncing the word cryptography. You will hear me struggle with this word. But no way, Jose. Who in this room has a clue what Jose actually stands for? One hand. Very, very good. It means that there's at least a few more people that I can teach what Jose is. And Jose, I will spoil it right now, stands for JSON Object Signing and Encryption. And if I ask all of you, who's ever heard of JSON Web Tokens before? Way more hands, and that's cool. Basically, Jose is a group of specifications which includes JSON Web Tokens, but it also includes a bunch of other specifications, which we'll see towards the end of this talk. But I cannot talk about JSON Object Signing and Encryption without first explaining the basics of signing and encryption, which are both cryptography thingies. So, who am I? My name is Bellen. I'm from Belgium, so I didn't come that far. I'm a developer advocate engineer at Alt0. I'm a Google developer expert, and if you want to find me anywhere on the internet, you can find me as Sambego. I am a developer, which only makes sense that I am also npm installable. So if you run npm/about me, download the internet, wait a few seconds, you'll find all the slides to my social media and to all of my talks right there in your terminal. These slides are available if you want to watch them later, tomorrow, next year, or right now on your phone. You can find these slides at jose.sambego.tech. The ones online are a bit more expanded than what I'm going to do today, just because I only have half an hour and I have so many things to say about cryptography. But these slides will always be here, and I'll share the link again after this talk. And a little disclaimer. I might simplify certain things in order to try to explain them in an easier way. Cryptography gets quite complex quite fast, and I'm only going to try and stay on top of all of the basics in this talk. Another disclaimer, please, please, please don't reinvent the wheel. If you have to do anything cryptography related, please use the existing solutions out there. Use the solutions and libraries that are written by the experts that know what they're doing. I'm not saying that you don't know what you're doing, but it's usually a slippery slope if you try to build your own in a lot of domains. So, what are we going to look at today? Signing, encryption, and Jose. That's the basic summary of what we're going to look at. And we'll start with signing. And signing, digital signatures offer all properties of keyed hashes plus cryptographic non-repudiation. Now, this used to have a chapter which explained hashes and keyed hashes, but for this talk, we'll just skip over this, and we'll go straight to the cryptographic non-repudiation. Now, who has a clue what cryptographic non-repudiation means? The same persons that just raised their hand with Jose. Very, very good. This is what Wikipedia has to say about non-repudiation. Non-repudiation refers to a situation where a statement's author cannot successfully dispute its authorship or the validity of an associated contract. So, who knows what non-repudiation means now? I still don't know. Well, I know, but it's a very, very vague explanation. What I think it means, or my simplest way of saying what it means is cryptographic non-repudiation means that we can prove whoever created the signature. Whoever created a digital signature cannot disprove that they created the signature just because of this principle, cryptographic non-repudiation. So cryptographic non-repudiation enables other parties, other than the person that created that signature, to validate and check the signature's validity. So either everybody in the room should be able to validate a signature that I have created, and I should not be able to dispute that I have created that signature. That's a basic principle of cryptographic non-repudiation. It's a basic principle of digital signatures. Digital signatures use public key cryptography, also known as asymmetric cryptography. And the signer creates a signature using their private key. A private key is something that you keep private to yourself. You should never share that with other parties. And if you want to create a digital signature, you're going to use that private key to create that signature. Linked to that private key is also a public key, and that's a key that you can share with everybody who needs access to your public key. It's a public thingy that is okay to share with others. And anybody can ask for my public key related to that private key and use that public key to validate my signatures, my digital signatures, and they can also prove that I created a signature because that public key is linked to my private key. A signing algorithm usually is a collection of at least 3 different algorithms, something that generates those public and private key pairs, something that creates a signature using that private key, and something that verifies signatures using a public key. And if we look at a very, very basic example, we have the input, the quick brown fox jumps over the lazy dog, and we want to create a signature based on this input. We're going to use the signing algorithm, in this case RSA, and together with my private key, and if we mix it all together with this algorithm, we get a signature. It's a thing you see coming out of this algorithm. A signature is never reversible. You should never be able to get to the original input of that signature. It should only prove that somebody created that input, that signature. If you want to validate that signature, you're going to take the input again, together with the created signature that you want to validate, run that through a verifying algorithm together with the public key related to the private key that created that signature. And if you input this correctly, and if the signature is correct for the input, you should see that it's either valid, or if it's not valid, you should see that it's not valid. But the important thing to remember here is that you're going to use a private key to create digital signatures, and you're going to use public keys to validate those signatures, and you can share those public keys with anybody, so anybody would be able to validate my public signatures. So the most commonly used public key cryptography approaches when signing are RSA. That's the most commonly used ones, but you also have elliptic curve, ECDSA, and Edwards curve, which are a bit more complicated, but those are the main flavors of public cryptography, of public key cryptography that we see these days. So, when are we using signatures these days? Whenever you use JSON Web Tokens, you might know that it exists out of 3 parts, and that last part is a signature, which basically proves that nobody tried to tamper with the content. That last part is a digital signature. When you sign some documents online, you're also going to create a signature based on the input, based on the document you're trying to sign. That was it. A very, very short, basic introduction on signatures, digital signatures. And I'm going to do the same for encryption. When encrypting data, we can not only ensure its integrity and authenticity. So again, we can not only prove that nobody tried to tamper with whatever we encrypted, and that is authentic, but the data will stay secure for outsiders. Now, proving integrity and authenticity can be done with signatures, but the data will stay secret for outsiders is something that is specific to encrypted content, just because you need to be able to decrypt the content in order to be able to see what the actual content is. There's a few approaches. You either need a private key, a secret key, or a password, depending on which algorithms you use to encrypt your data. And the encrypted message is also often called a cipher. So when you hear me say the word cipher, that's whatever comes out of an encryption algorithm. It's the encrypted message, it's the encrypted data. There's 2 kinds of encryption mechanisms. There's the symmetric and asymmetrical ones, and we start with the simplest one, symmetric encryption. And a few examples are when you want to encrypt your whole file system or all of the data on your Wi-Fi networks, or maybe you want to encrypt all of your database or certain parts of your database. Usually when we deal with big chunks of data, we try to use a symmetrical algorithm just because they're a bit simpler, they're a bit faster to use. So the most commonly use cases are the use cases where we deal with big chunks of data or chunks of data that we don't know how big they will be. And some of the algorithms are direct AES, AES key rep, and AES GCM. But how does this work? Same example as before. We want to encrypt the quick brown fox jumps over the lazy dog. And again, we have an encryption algorithm and a decryption algorithm. And when you run that input through the encryption algorithm, you get your cipher. And you run that cipher through the decryption algorithm, you get back to the original input. So this is different from digital signatures, where a digital signature should be a one-way function. You can never get back to the original input from a signature. That's also not its point. It's just the point of a signature is to prove that the actual input is valid. It's not been tampered with. A encrypted message can always be reversed to the original input just because we want to share encrypted messages with others, and these others should be able to decrypt these messages in order for them to read the message or consume the data. But the thing with symmetrical algorithms is that they use a shared secret, a password, one single credential to both encrypt and decrypt that data. So if you have possession of that shared secret, you can both encrypt and decrypt the encrypted message, the cipher. In asymmetric encryption, on the other hand, we're not going to use one shared secret, one password, one secret. We're going to use a public and private key pair again, just like we did with the signatures. But this works the other way around. With signatures, we use a private key to generate a signature, and anybody can use my public key to validate my signature. When you want to encrypt some data using a public and private key pair, you're going to ask for somebody's public key and use that public key to encrypt the data. And once you have encrypted the public data with somebody's public key, you can send them the encrypted message, and they will be able to use their own private key to decrypt that message and see the actual message that has been in that decrypted cipher. So it's a little bit of a mental shift. Signatures, you use a private key to sign and a public key to validate. With encrypted messages, you use a public key to encrypt and use a private key to decrypt. So, again, the same example, the great quick brown fox and so forth, but you'll see that we don't use a shared secret anymore. We use a public key to encrypt. And if we want to decrypt that message, we can use the private key belonging to that public key, or the other way around, to decrypt the actual message and get back to the input to read the actual decrypted or encrypted message. Cool. Asymmetric encryption. Some example use cases: TLS, VPN, SSH, a lot of acronyms, but I think we've all seen this in our lives. We use this in a lot of instances without even realizing that we do. And some of the algorithms, most of them are RSA related, but you can also have elliptic curve or Edwards curve, just like with signing algorithms that deal with asymmetric algorithm or asymmetric encryption. So let's look at a detailed example, because it's all fancy, it's all good that I'd say to you, you just input into an encryption algorithm together with a public key and you get a cipher, and then if you put it in the decryption algorithm together with the private key, you get your text back. But how does this actually work? Let's look at a detailed example on how RSA work. Each of these algorithms have different ways that they work, but they all work on a set of mathematical principles. And the first thing we need to do with RSA is generate the public and private key pair. So, a small note, again, this is a cryptography presentation. I have to do a lot of notes and disclaimers. Cryptography is usually based on an algorithm using very, very large prime numbers. RSA is no exception. And when I say large prime numbers, do I mean 1 million? Do I mean 1 billion? Nope. I mean something that's this, and it doesn't even fit on screen, I think, because it should be more digits. But this is 1 million, this is 1 billion, and you can see that it has a lot more digits. It often has 150 to 300 digits. I don't know the name of those numbers, but they're very, very large prime numbers. In my example, I'll use very, very small prime numbers, just for demonstration's sake, but know that in practice, you will use very, very large prime numbers for this to be a secure way of encrypting or signing data. So, if we want to generate our public and private key pair, we're first going to generate 3 secrets. The first 2 are 2 of those very, very large prime numbers. In this case, 61 and 53. Again, in practice, this will be very large numbers. Here it's 61 and 53, 2 prime numbers. And based on these 2 prime numbers, we're going to generate a third value called lambda. It's just the least common multiple of the prime number 1 and prime number 2 minus 1. You don't have to know the math. You just have to know that we generate 2 prime numbers, and based on those 2 prime numbers, we generate a third value, and we keep those secret. We're not going to share this with anybody. We're just going to use these to generate our public key and private key. Then in our public key for RSA, we have a modulus and a public exponent, where the modulus is the first prime number times the second, and the public exponent is the coprime of that lambda value. And the private key contains, again, that modulus, the same as the public key, but instead of a public exponent, it contains a private exponent, which is the outcome of that mathematical function you can see on screen. Again, you don't have to look at the math, you don't have to understand the math, you don't have to remember the math. Just know that both of these public and private key pairs are based on the same values that we generated, and that we can forget as soon as we have generated these public and private key pairs. Cool. We've done the first step. We have a public key, we have a private key, so we should be able to use a public key to generate an encrypted message, and we should be able to use the private key to decrypt a message. So let's start by creating a cipher. Let's start by using the public key to encrypt a message. Now, if we have the input 1 to 3, a very, very simple input, and we run this through the encryption algorithm for RSA, we'll see that we have a mathematical function again. And if we input this together with the modulus, the n value, and the exponent, the public exponent e value, you get another output, which is 2183. It's the mathematical outcome of this algorithm. So let's remember 2183. But in most use cases, you're not going to deal with mathematical numbers. You're dealing with real data. This might be text, this might be binary, this might be anything else. So we first have to do a lot of data conversion. But under the hood, it's always going to be mathematical functions. So we borrow this data like a string down to mathematical numbers, and then use these algorithms based on these mathematical representations of our data. Cool. Remember the number that we got out of that encryption algorithm? If we now want to take that number and get back to the original input, 1, 2, 3, 4, we're going to run this through a decryption algorithm, the RSA decryption algorithm in this case, together with the private key that we generated a few steps back. So we take 2183, which was the outcome, which was a cipher, run it through the decryption algorithm, which is again a mathematical function, together with our private key data, our modulus, and our private exponent. And if all of these pieces fall into place, if they're all correct, we should be able to get back to the original data, which is 1, 2, 3, 4. So in this example, if you don't believe me, the math was correct. So it's all mathematical stuff under the hood. Again, usually you're not dealing with numbers, so you need to do some data conversion, but under the hood, you're always going to use those mathematical algorithms. This is just a very simple explanation of RSA, elliptic curve, Edwards curve. All of the other flavors out there use other math. Most of them are a bit more complicated than RSA, but it's all math under the hood. And I created a little playground for this, or a little interactive tutorial. And if you're interested in learning a bit more about RSA or reading, again, what I had to say just now, I created rsa.tech, which is still a work in progress, but I'm ready to share it with you anyway. And if you type any message here on the top, let's say test, you'll see that we get an encrypted message in a few different formats. And one of them is that integer. This is the mathematical or the integer representation of this word text or test. But under that, you'll see that we generate 2 prime numbers, 1 and 2. And then the lambda version is going to be a very, very large number. We generate the public key and the public exponent, and then again, the numbers for the private key. And then it walks you through how we're going to use all of these numbers. And you can see the math before you appear based on the input that you gave at the top. So if you're interested in learning a bit more about RSA, rsa.sambigo.tech, I will share these slides and this link again after this talk, so you don't have to look at it right now. But this is a Jose talk. It's in the title, No Way Jose, JSON Object Signing and Encryption. So let's look at what Jose actually is, apart from what I already spoiled, JSON Web Tokens. So I mentioned JSON Object Signing and Encryption. Why JSON? Well, JSON format is often used for serializing and transmitting structured data over a network connection, which means we use JSON on the internet the whole time, all the time, always. It's way more readable than certain other formats like XML, for example. And it has excellent support in most programming languages. We're at the Angular conference. I think all of us know at least a little bit of JavaScript, and it has first-class support in JavaScript because it comes from JavaScript. So that's cool. That's why we use JSON. And it contains a lot of JSON Web somethings. JSON Web Tokens is the first example, but let's start with JSON Web Keys. And a JSON Web Key is just a JSON representation of either a private or public key, and depending on which algorithm you're using, which approach you're using, this will contain a bunch of data. But if we look closely at what's in this JSON object, we see a few things. It tells us it's for the RSA 256 algorithm, and it tells us a few other things like the N and E value. And if you remember when we generated the public and private key pairs in the RSA example, we had an N and E value being the modulus and the public exponent. Should this be a private key, it should have the modulus and the private exponent. So a JWK, a JSON Web Key, is just a JSON representation of all the data you need in order to consume that key, being it a private key or a public key. The next one are JSON Web Signatures. And this might look familiar to those that have seen JSON Web Tokens before. And that is because most JSON Web Tokens are actually JSON Web Signatures used as a token. And most all JSON Web Signatures contain 3 different parts. The first part, the second part, and the third part, and they are separated by a dot, where the first part is just a base64 encoded JSON object we call the header. The second part, the base64 encoded JSON object we call the payload. And the last part is a signature that proves that that payload and that header have not been tampered with, other than the creator is able to change its values. So the Jose header just tells us which algorithm we use to create that signature. That's all it does in its most minimal form. Sometimes it has a little bit more information, but all it needs to tell you for you to consume a JSON Web signature is which algorithm to use to validate its signature. The payload is whatever data you want to sign. So anything valid JSON is fine. You can put in strings, you can put text, objects, arrays. As long as it's valid JSON, you can put it in that payload. And then again, that signature is the signature that proves that nobody tried to tamper with that header and that payload. So for example, we take HMAC SHA-256, which is actually a keyed hashing algorithm, but most of the time we take signing algorithms. We run it through we run the header and payload through that algorithm together with the secret, and we get a JSON Web signature, or we get a signature. That's it. JSON Web Signatures. It's just a JSON representation, or it's a string representation of 2 JSON objects, being it a header and a payload. Next up, we have JSON Web Encryption, which is a little bit more complicated, but I'll try to go through it as fast as possible and as easy as possible. But instead of using 3 different parts, we have 5 different parts. The first one is familiar. It's a HOSE header, a base64 encoded JSON object that tells us a bit more about this JWE. Then we have the JW encryption key, or encrypted key, the initialization vector, the cipher text, and the authentication tag. And the good thing to know is that JWEs use 2 kinds of encryption. We've seen that there's 2 kinds, symmetrical and asymmetrical ones, where one flavor uses public and private key pairs, and the other one just uses a shared secret for both encryption and decryption. A JWE uses both of them in combination to be as secure as possible. So, the content encryption key is usually encrypted with an asymmetrical algorithm, which means that the content encryption key, the second part of the JSON Web Encryption object, needs to be decrypted first before we can encrypt the actual cipher. And this is encrypted with an asymmetrical key because it's a small piece of data, it's just a key, so we know that it's not going to be a huge piece of data. And if we want to decrypt this, we are going to wait a few seconds until I get to the slides. But the cipher is then encrypted using a symmetrical algorithm using that content encryption key that we have to decrypt first. So let's first look in the HOSE header. It tells us a few things. 2 algorithms, a symmetrical one and an asymmetrical one. And it also gives us a key ID so we know which private key we need to use whenever we want to use that asymmetrical algorithm. So the first thing you need to do when consuming or when validating or when decrypting a JWE is decrypt the content encryption key, which is that second part of that 5-part string. So we're going to look in our header. We need the RSA OAP algorithm in this case. We're going to take a library that knows how to deal with that algorithm together with the content encryption key, which is that second part, and the private key of which we find the ID in the header as well. And if we input all of the correct things, we would get a decrypted content encryption key. This is just a password, a shared secret, something that you can compare to that. But we need that. We need that shared secret, that content encryption key, in order to decrypt the actual cipher, which is that 4th part in this string. So if you want to decrypt that cipher, we're going to look in our header again. We see that we need to use this algorithm. We take a library that knows how to deal with that algorithm. And if we input our cipher together with our decrypted content encryption key, our initialization vector, which is the 3rd part, and our authorization tag, which is the last part, we should hopefully get our decrypted JSON Web Encryption object. We should get our decrypted message that we wanted to share encrypted with anybody out there. So both JSON Web Signatures and JSON Web Encryption can be serialized as compact. What that means is that we've seen up until now that JSON Web Signatures are a string consisting out of 3 parts, and a JWE a string consisting out of 5 parts. But they can also be just a bunch of JSON, just like the JSON Web key that we saw in the beginning. And this would be a JSON Web Signature serialized as JSON, but we see we still have the same data. We have the payload, we have the header, we have the signature, it's all in there. And this is a JSON Web Encrypted object in the form of JSON rather than as a string. And again, it has the header, it has the initialization vector, the cipher text, the authorization tag, and so forth. So it's the exact same information that we saw, that we extracted from those large strings, but then represented as JSON. Lastly, JSON Web Tokens, I already touched on this. And a JSON Web Token can either be a JWS or a JWE. And this is a funny thing, because when we think of JSON Web Tokens, we think of that string that consists out of 3 parts, but it doesn't have to be. It can also be that longer 5-part string if we really want to encrypt the data in that JSON Web Token. Most of the time, that's overkill, and most of the time, we use a JSON Web Signature, but the JWE is also fine. But they're always going to be serialized as a string. You're never going to use that JSON object of these signatures or encrypted messages for JSON Web Tokens. It's always going to be that compact part. JWS is more common. Like I used, most of the time encryption is overkill, but you can do it if you want to. So let's look at some header. A JWT header is exactly the same as a signature or an encrypted JWE, but it also tells you that I am a JSON Web Token. That's the only difference. So if we look at a few examples, an access token, I don't have much time, I know, sorry. We see some information in the payload that is related to an access token, which is related to accessing an API, things like who issued it, which user it's for, which API it's for, and so forth. If we look at an ID token, it contains some information about a user because it's related to the identity of somebody that authenticated. And if we look at something like a depop proof, a depop is basically a way of telling that somebody is allowed to use an access token. So it tells us that some information, if somebody has this proof, it should be allowed to use an access token. But it's all just JSON information that we can put inside of the payload of a JSON Web Token and send with a request over the internet. So let's summarize. Keyed hashes, we didn't talk about that today. Digital signatures allow third parties to verify the validity and origin of data. Encryption allows only authorized people to read the data. You need to be able to decrypt an encrypted message in order to read the actual data. JWT is a set of standards based on JSON that helps us with signatures and encryption on the web. That's it. If you want to see the slides again, jose.sambigo.tech. I'll tweet them again later as well. JWT.io will teach you a little bit about JSON Web Tokens and let you debug them. rsa.sambigo.tech is this little playground created to teach RSA. If you're interested in the SHA-256 algorithm, this website teaches you all of its complexities. Thank you very much.